Hi everyone, I'm going to tell you about our work on optimally improving cooperative learning in a social setting. This is a joint work with Cheng-Jin and Jiego. Consider a situation when we have a set of network agents who solve a common classification problem, but they have their own individual learning models. For example, consider an online social network and assume that each of the agents are trying to assess whether a content is AI-generated or no. So they use their own individual models for the prediction of the label of this content, but after the prediction is made, they may exchange their predictions. We can think about this model in different contexts. For example, if we have some financial agents who are making the same prediction about the stock value of whether it is overpriced or no. Or we can consider a security system when each agent wants to assess whether a network is under attack, under a cyber attack or no. To model this problem, we consider function f with domain omega, and the labels are -1 or +1, and we have a set of network agents. Each agent owns its own classifier, fi, so you may have f1, f2, f3, and more. Nature samples one element from the domain, and all the agents use their own classifier to make a prediction. Then through the network connections, the agents exchange their predictions and update it to a new value, z star. So if the true value is +1, positive value of z star means high accuracy. If true value is -1, negative value of z star means high accuracy. By multiplying these two, we obtain an accuracy measure. Now, our goal in this paper is the study of the following problem. We have a social planner who knows the true label, and he or she wants to select a subset of the agents and improve their predictions. We assume this improvement is a linear combination of the true label and the label predicted by the old classifier. Once these agents are improved, we will have an impact on the whole social network, and the accuracy of all the agents will go from z, the old z, to the new z. Okay, let me summarize the results here. In this paper, we consider two different objective functions. One is an aggregate improvement, and the other one is an egalitarian improvement. In the aggregate improvement, we are looking at the sum of the improvement in accuracy of all the agents. And we show that this problem is easy in the sense that we have a polynomial time algorithm for it. For the egalitarian improvement, we consider the agents which have a very bad accuracy, negative accuracy, and we ask whether they have a non-zero improvement. This problem, we show it's NP-hard. For the second problem, we devise two approximation algorithms. The first algorithm assumes full access to the joint probability distribution of classifiers. Its runtime grows linearly with the size of the domain, which is not very desirable. In the second algorithm, we assume that the agents have pairwise independence. Here, we just need the error rates, and the runtime is not dependent on the domain anymore. It's just growing with n cubed, and the approximation ratio is a little bit lower.
Our proposed greedy algorithms iteratively picks new agents by optimizing some carefully designed marginal gains. Such marginal gains essentially depends on information related to error rate of each agent and edge weights of the whole network. So in the experiment part, we compare our proposed algorithms with baseline heuristic algorithms, which pick agents according to information, including no degree and error rate, and also random algorithm. So we test all these algorithms on a diverse synthetic and real-world graph datasets. Our empirical results show that our proposed methods perform better on these datasets compared to the baseline method. So in general, we can see that our proposed algorithms can achieve more than 90% accuracy with only log n agents picked up on most of the datasets. So to summarize, in this work, we introduced a new model in which network agents cooperatively improve their learners by solely exchanging their predictions. So our theoretical analysis and experiments show potential applications of our methods to diverse domains, like social network analysis, or cybersecurity, and so on. So in the future, we would like to expand this work along several directions, including considering negative edge weights, other improvement objectives, and more general agent learners. Okay, thank you.